Thank you for the introduction. So I assume you are pretty familiar with WhatsApp. It's a messaging application that is used by a lot of people who send a lot of messages. And we have some core values to be simple, reliable, and private. And at Meta in general, we have a bunch of tools that help developers write robust code that satisfies these properties. But in this talk, I will be focusing on WhatsApp server specifically, which is written in Surprise Erlang. And we do have some static analysis tools that we already apply, some basic linters, or the equalizer type checker that was just presented in the morning as the keynote. And we also have dialyzer, actually the incremental version, of which, if I'm correct, there's going to be like a lightning talk by Tom after this one. But we realized that like these tools didn't provide analysis for all the properties that we were interested in. So we turned to Infer, which is basically an open source static analysis platform developed at Meta, where in the past couple of years it has been running on tens of thousands of code changes monthly, reporting thousands of issues. And it already had language front ends for C, C++, Objective-C, Java, and C#. But with this work, we also added support for Erlang. And also in Infer, you have more than 20 different kinds of analysis, ranging from memory safety, data races, to time complexity, deadlocks, and temporal properties. So this is what we started with. And in this talk, I'm going to present you how we extended Infer to support Erlang, and how we applied it to the static analysis of WhatsApp server. I'm going to start with a few examples to show what the tool can do. Then I'm going to mention some challenges with analyzing Erlang code with Infer. Then I'm going to dive a little bit into the compilation and analysis details. And finally, I'm going to present some results about applying it to WhatsApp server. So let's start with a few examples. To be more specific, some user-specified properties. Let's say we want to check whether we ever write to a file after we closed it. This is a temporal property, and in Infer, if we want to check this, we have to formulate this as a temporal automaton. We have a start state where we can either loop. So this is a non-deterministic automaton. This is required so that we can track multiple files at the same time. And then if we see a call to file close with a certain file, then we remember this file and we go to the close state. And in this state, if we see a call to file write, where the file is the same one that we remembered, then we go to the error state because we call the write after close. So this is the automata, and we can actually put it in a textual format, but this is the boring part. This is how you describe this automata. But then if you have some example Erlang code, like the one that you see here, there's two main functions, good and bad, and both of them write to the file, but before that they do something. Good does nop, which actually doesn't do anything. Bad does op, which closes the file. And to check this with Infer, in order to check this, we actually need interprocedural analysis. And to check this with Infer, you can use this command. Basically, you type Infer, you specify Topple, which is the analysis that supports temporal logic properties. I will get back to this later. But then you specify the property and you specify the build command. And then Infer will tell you that there is a problem in the bad function, which indeed there is a problem. As another example, let's consider Taint Analysis. So let's suppose that we have some source and we have some sink, and we want to know whether the return value from the source can ever end up as the argument of the sink. We can also formulate this with a similar automaton, We have a start state where we can loop non-deterministically to be able to track multiple tainted values. And then if we see a call to a source function from some module, we can use regular expressions. Then we return this. Then we remember this return value being dirty, and we start tracking. And if we see a call to a sing function, again any kind of sing function where the argument is dirty, then we go to the error state. And so this doesn't. This can analyze taint properties, but this doesn't account for transforming the data. So if we want to support transformations, then basically in the tracking state, we have to add the loop, which tracks all sorts of transformation functions that we are interested in. This is where probably regular expressions help the most. And as of now, if we want to track taint properties across data structures as well, we have to add a few built-in functions. Basically in Infer, like data structures, such as constructing a tuple or a list, is translated into these special functions, make tuple, make cons. And with these regular expressions, we can track tainted data across data structures as well. And so besides these user-specified properties, we can also check some of the standard Erlang errors. We call these reliability issues. So for example, if you have this head function here, which either returns empty or a tuple of awk and head, and there's a few use cases like good will match and all the others will crash, then we can also run Infer on this. For this, we use the pulse analysis. I will get back to this later, but this is what provides analysis for these reliability properties. And again, we provide the compilation command, and then we get a list of the potential crashes. And besides these, we support some of these standard errors like bad key, bad map, bad record, and all sorts of pattern matching problems. These are very similar to what Dialyzer does, and this is not really the main focus of our tool. We are really targeting these user-specified properties, but since we had the framework, this was quite easy to implement, so we added support for this. And I would say that compared to Dialyzer, which is very, very under-approximate, Infer is still under-approximate, but a bit less, but I will get back to that in more detail later. So let's talk a little bit about the challenges. First, let's just revisit our context. So we are working in Infer, which is the static analysis platform, and it already had support for Java and a few other languages, but these were all mostly imperative and object-oriented languages, and Erlang is functional, so it's like a conceptually different language. And it also had some built-in analyzers, like I was mentioning, Pulse and Topple. I will get back to these later as well. And also, one very important thing about Infer is that it uses a compositional bottom-up interprocedural reasoning, which means that it analyzes procedures in isolation, it computes summaries, and then when one function calls another, it uses the summary of that function, which, as you will see later, is quite challenging in the context of Erlang. So basically, the first main challenge is that Erlang is functional. You have higher order functions, closures, recursion all over the place. And also there's no implicit notion of variable declarations. So for example, with closures, we have to do some scope analysis to figure out if a variable is captured or if it's local. So if you have this, for example, you have this typical map function here, and then in the main function you pass in some lambda, then we had to figure out whether this x is local or whether it's the same one as here. And also coming back to interprocedural compositional analysis, if you are analyzing this map function in isolation, you don't really know what this function f can be. And it makes really hard to reason about the code of such functions. Then in Erlang, you have this let it crash philosophy. Basically, it's quite hard to distinguish between user thrown errors and runtime exceptions that should not happen. And this is especially challenging with supervisors. So often it is fine for a code to crash because some supervisor will later catch it and restart it. But in the context of a local compositional analysis, this is very hard to figure out. So for example, if you have a head function like this, it's not really clear whether it is intended to crash for an empty list or not. Then, as you know, we have dynamic types. And as opposed to the other languages that Infer already supported, dynamic types are used quite frequently in Erlang. Basically, every pattern match is usually has something to do with types. And again, connected to the let it crash philosophy, it is rarely complete. So if you have like a lang function like this, it only works for lists, but will crash for anything else. And again, it's not really clear whether this was the intention or whether the developer just forgot to add some clauses. And then we have concurrency. And as opposed to other languages already supported by Infer, Erlang was designed with concurrency in mind. Basically, you have primitives for sending and receiving as first-class citizens in the language, and you also have all sorts of high-level abstractions like state machines and gen servers and this kind of stuff. And finally, scalability, which is always a challenge in all sorts of program analysis, but I would like to point it out here because WhatsApp server is huge. We have millions of lines of Erlang code, and we want to provide early signals to developers. And in general, Infer is pretty good in terms of performance due to its under-approximate compositional analysis. But for certain Erlang-specific constructs like data structures like lists or list comprehensions, we had to come up with some Erlang-specific abstractions to keep this efficiency of Infer. So let's take a look a little bit at the compilation and analysis, starting with the basics. So in Infer, you have two main phases. You have the capture phase, where the different language frontends compile source code into Infer's intermediate representation called SEAL, which is based on control flow graphs annotated with instructions in the nodes and on the edges. And then in the analysis phase, you have different checkers that can run on this intermediate representation, like, for example, the pulse that I was mentioning. And ultimately, it outputs the issues to the console or to some file or database. And to add support for Erlang, obviously, we had to add an Erlang frontend. And we use ERC and rebar3 to take the Erlang code and compile it into Beam files with some special flag that will preserve the AST in the online. Okay, so I think I was at the point where I mentioned that we compile the AST that we get from the Beam files into the intermediate representation. But then for certain built-in data structures or like built-in functions, we had to add some custom models to the analysis so that it understands the semantics of this Erlang stuff. And as you will see later, we can also use some user-defined models to like alter the behavior. And then we also have the Topple Analysis, which is for temporal properties. We had to extend and improve this significantly. It is actually built on top of Pulse. And as you've seen, it takes the user-defined property, the automata, as an input as well. And we can also parse type specs from OTP. I will get back to this later again. This will be important to eliminate some false positives. And finally, we have the reporting phase at Meta, which basically consists of some signal boosting, matching against production data, ownership attribution, so that ultimately, in the end, we end up with the signals to the developers. So yeah, this is the architecture. And let's talk a little bit about this part, the actual compilation. So if we have our head function from before, which returns either empty or the tuple of awk and the head, then in Infer, for each function, we get a procedure with the appropriate number of arguments. Here we only have one, argument 0. And then we go close by close. So first we check whether the argument is nil. And if it is, then we construct the atom empty and we return it. Otherwise, we move on to the next clause. We check whether it's a cons, and if it is, then we get the head, we construct the awk atom, and then we return them together as a tuple. And then, since we have no more clauses left, we will return the no matching, or we will report the no matching function clause error. So this is like how roughly translating one procedure works. And then on the analysis side, as I mentioned, Infer is working based on summaries, which are computed once per function. And basically, they are a compact representation of interesting behaviors. They are somewhat similar to these pre and post conditions that we've heard in one of the earlier talks. So for example, for this head function, we could infer three summaries. The first one is that if it's a nil, then the precondition is that it's a nil. The post condition is that it returns empty. Then we have one for cons, and then we have the error state when the argument is neither nil nor cons. So these are the three summaries that we get for this function. And the important properties of the analysis is that it is modular, which means that we analyze one procedure and its dependencies at a time. And it is compositional, which means that you have to only compute the summary once, and you can apply that in different calling contexts. So for example, if we have a function foo and we want to compute the summary, and then we figure out that, well, this function actually calls the function bar, then we compute the summary of bar first. We put it in the database so that later we can use it to compute the summary of foo. And obviously this doesn't work if we have cycles in the dependency graph, as for example with recursion, but I will get back to this a little bit later. And under the hood, I mentioned that we use the pulse and the tuple analyzers, and they are based on incorrectness separation logic, where incorrectness refers to the fact that they are tailored towards bug finding rather than proving correctness. And they work with these under-approximate triplets that you've already seen. So you have some precondition, and then if you execute that code, you can reach some resulting assertion, either with OK or with some error. And under-approximation means that if you would execute the concrete code with the possible states of the precondition, they form a superset, what is actually described by the result. So basically, every state that is described by the resulting assertion can indeed be reached by the program. But there might be some states that can be reached, but we don't include them in the resulting assertion. So this is under approximation. And if you want to read more about this, then there's a bunch of papers already published by the Infer team on this topic. So let's dive a little bit into the details. I was talking about this problem of non-exhaustive pattern matching and the let it crash philosophy and dynamic types. So for example, for this lang function, it is not clear whether it is intended to crash on any type other than lists. And normally Infer would report an error in this case. And to avoid this, we use type specs, as you've seen in the keynote. WhatsApp server and also OTP is quite well annotated with type specs. So we can, with this fact, Infer can figure out that the pattern matching is complete modulo the type specs. And we also use it to model the return value of functions from OTP for which we don't explicitly provide a model yet. So for example, for lists sort, if you don't know what it returns, then this could be non-exhaustive. But if we actually know the specs that it returns a list, then Infer can figure out that, again, this is indeed complete with respect to the specs. As for data structures, I mentioned that we had to add support in pulse. And for tuples and records, we have full support. For lists, we often translate list operations into loops. And for that, Infer automatically applies some approximation by specifying a fixed loop unrolling bound. But so far, it has worked well in practice. And for maps, we use a recency abstraction, something very similar that they also do in Java, which means that we only store the most recent key and value. And this is basically suitable to avoid false positives when someone checks whether a key exists in the map before actually trying to access it. But then we can report issues if we are just trying to get the key without checking whether it's there or not. And so for all the higher order stuff, for closures, we have some limited support. We support them in a local context. And for that, we actually had to do a scope analysis to determine whether a variable is captured and local. And we actually found an interesting bug in the compiler, because if you look at this example, there's a plus operation, and on the left-hand side, you assign or you bind x to be 1. And on the right-hand side, you have a lambda, which binds x to be 2, then calls the lambda. And if you put this code in the interpreter, it would evaluate both sides of the expression independently. So that would be like 1 plus 2, resulting in 3. But if you actually put this in a function and compiled and try to run it, then the compiler would do left to right evaluation. So it would first bind x to 1, and then here when you would try to bind it to 2, it actually crashed. So we submitted an issue, and since then this was fixed by a pull request, and it was the interpreter which was determined to be right. So now the compiler was adapted to act like the interpreter and treat these sides independently. I guess my main point with this is that it was not trivial to even for us to figure out what's happening, and even in the compiler, this was not something well defined. And so for other stuff like recursion and unknown closures, so for unknown closures, there's like two possibilities. One of them is specialization, which is already there in Infer for Objective-C, because Objective-C has lambdas, which are very similar. And basically, specialization means that if you have this function g, which can call some function f, and in the main function, then it's hard to analyze this in a compositional way, because you don't know what this f could do. But if in a main function you see it with some concrete function f, then you could basically specialize both g and both the main function to these concrete instances, and then you can provide some summaries. But also defunctionalization can work. I'm not going to go into the details. You can read this paper, but that is basically a whole program transformation which can remove closures without changing the behavior of the program. But since Infer is not a whole program analyzer in general, or that's not the philosophy, probably the route that we will go down will be specialization. And it also works quite well for Objective-C. And recursion is also interesting. As I mentioned in the dependency graph, if you have cycles, then you have to break them somehow. And previously, Infer actually had some iterative fixed point computation, but then it was removed because it was quite complex. And for most of the other languages, developers were happy with those bugs that Infer found by only running one iteration of fixed point computation. So basically no fixed point computation at all. But we might bring that back for Erlang, although it would have some performance penalty, obviously. But one thing that could also work is to basically provide some custom models, especially for standard library functions. So, for example, a map function could be modeled in Infer in an iterative way, and many of the library functions. So in practice, that could also work well. As for concurrency, as I mentioned, concurrency is a first-class citizen in Erlang, and right now we treat send as a no-op, like nothing happens, and for receive we treat it as non-deterministic, so we can receive anything. But we have some plans to basically generalize function calls, because if you think of it, when you send a message and then wait for receive, it's kind of like calling a function. It's just you have to figure out like which send corresponds to which receive, and basically for each receive you could compute a summary that you could use when you send a message and then wait for a reply. And again, if there's like multiple processes sending messages back and forth, then you might again need to do a fixed point computation similarly as if they were mutually recursive function calls. For high-level abstractions like Gen servers, we don't support them yet, but we also have plans for these. Gen servers are often used to implement behaviors like distributed objects and actors, and Infer already has support for objects in various languages. So like spawning, initializing a server, then looping and exiting is very similar to constructing an object and then receiving function calls and then destructing the object. So that's the plan there. For library functions, we do have models for some of them, like list, reverse, maps, get, whatever. But then for most of them, we don't have any models. And as I mentioned, we use type specs from OTP to avoid reporting many false positives related to pattern matching. But we also provide support for user-defined models. Right now, we have a JSON-like syntax where we can specify that if we see in some module a function with the name complicated function and arity 0, then its behavior should be that it returns a tuple which has an atom of true and null, which means a non-deterministic value. So with this, we can basically specify that as if this complicated function would look like this. And here the plan would be to add more kinds of behaviors and also to be more user-friendly instead of this JSON syntax. There is actually some work going on this to specify it in Infer's intermediate language, but ultimately it would also be nice to be able to specify it in some subset of Erlang. And I mentioned that besides the pulse analysis, we use Topple for the user-defined temporal properties. And this one we had to significantly improve and extend because it has already been there in Infer, but it hasn't ever been used at such a scale what we have at WhatsApp. So the problem was that we often hit internal limits during exploration because, for example, because of this non-deterministic branching, we had many states where these red ones denote those ones which are actually not satisfiable. And this led to false negatives because for performance reason, Infer has some cutoff limit after which it just gave up analyzing procedures. And then we actually missed legit states that could, cause like a taint issue or whatever. So here we did some improvements, like we trigger some more expensive normalization selectively. We added better support for dynamic types because, again, for the languages that were already supported in Infer, this was not as important. And we also did some garbage collection for values that we don't use anymore. And with this, we could really push the limit by eliminating some infeasible or uninteresting states so that we could analyze more states where we could get meaningful results. So finally, let's talk a little bit about the results. First, I want to mention that we developed like more than 700 small test functions, which are also available open source. These are some small snippets that exercise a specific feature and then either pass or deliberately crash. And what we do with these is we compile and run them. So we get like either a pass or a crash. And then we also analyze them with Infer. And Infer will also either say that the function is OK or it will report an issue. And if the two matches, then it means that we have a true negative or true positive. But if there is a mismatch, then we have a false positive or a false negative, assuming obviously that the compiler is always right, which, as you have seen, it is not always right. But still, for these test cases, what we would like to make sure is that the semantics of compiling the code and running it is the same as how Infer interprets it. So this gives us a lot of confidence that we got the semantics right. And if you want to make some changes, it's very easy to run all these tests and make sure that we don't break anything else. But what is more interesting is that we also applied this to WhatsApp server. And initially, we started with the reliability properties because when we were developing the front end, those kind of properties were the first and easiest ones that we tested them with. And well, with these reliability properties, we still have many false positives, because even though Infer is under approximate in nature, if it sees some unknown functions, then it treats the return value as a non-deterministic value. So in that sense, there is still some over approximation there in the semantics. We are working on reducing this, but what is more interesting is that we deployed some taint properties. We found, as of the writing of the paper, we found like 200 issues with taint, and we were running it over the existing code base, so not on new changes at that point. So we could also apply prod matching, which means that we matched the taint flows against production, like whether they really ended up in the sinks. And with this, we could actually surface 21 issues to developers. And so far, as of writing the paper, 3 of them were fixed by developers, 2 with high priority, and 1 with very, very high priority. So it provided useful feedback to developers. And one thing that we also do is signal boosting. We also have a dynamic analysis based on test generation and traffic generation running. This was presented this year at ICST. We have this dynamic analysis called FAUSTA, and we also do signal boosting. So if one analysis found an issue that another analysis has already found, then we basically extend the information. So we don't report duplicates, we boost the existing signal. So yeah, to summarize, I presented InfERL, which provides a scalable and extensible static analysis for Erlang. And we can check some of these standard reliability issues, but also we are mostly focusing on user-specified properties, such as taint, for example. And we had a bunch of challenges in the context of Infer, like Erlang being functional, the ladder cache philosophy, dynamic types, concurrency, and also scalability. And basically we developed both the front end that was needed to compile Erlang code into Infer's intermediate representation, and we also had to make extensions to the existing analyzers, Pulse and Topple. And we got some promising results on WhatsApp server after this initial deployment. It provided useful feedback to developers because we already detected some issues that were identified and fixed. And it is available open source as part of Infer, but most of the Erlang specific stuff lives in that subtree of the repository. Thank you for retention. And I'm open to questions. Thank you for the talk.